I'm Professor Graham Town from the Department of Electronic Engineering here at Macquarie University, and I'm pleased to welcome you to the Engineering Week lecture for 2011. I'll be chairing the proceedings this evening. Just a bit of housekeeping. Although registration wasn't required, we would like to record attendance, so there were some attendance sheets outside. If you didn't sign those on the way in, I'd appreciate it if you could do that on the way out. I should also mention that this event is being recorded and will appear on the university's YouTube site. I'd also like to express our thanks to Cochlear for providing this wonderful venue for the event this year. Thanks very much for that. And before calling on the Executive Dean for the Faculty of Science, Professor Stephen Thurgate, to introduce our lecturer for this year, Peter Ferris, I'd first like to give a bit of background to the Engineering Week lecture event. The undergraduate program in engineering at Macquarie commenced in 2004, and since 2006 the university has been sponsoring Engineering Week and also hosting these annual lectures as part of the wider Engineering Week activities, which are of course organised by Engineers Australia. And I should add that details of other Engineering Week activities for this week can be found on the Engineers Australia website. The aim of the Macquarie Engineering Week lecture has been to provide a forum for a prominent engineer or technologist who's been closely associated with Macquarie University to speak on a topic which is close to their heart. And some previous speakers have been Professor David Skellen, who was then CEO of NICTA and a former professor here on embedded systems, Dr. Cathy Foley, who's now the Chief of the CSIRO Division for Material Science and Engineering, John Chapman, who is the New South Wales General Manager for Siemens, who spoke on megacity challenges. And last year we had Professor Neil Westy, another former professor from Macquarie University, who spoke on immersive engineering. So it's clear that our speaker tonight is in good company. Excuse me. And I can say that in his own way he's made a significant contribution to the development of engineering at Macquarie and also to telecommunications infrastructure in Australia. And I think his topic tonight is of wide interest. There will be time for questions at the end of the lecture, so I'd appreciate it if you could hold questions until then, and I'll have a microphone to pass around to assist with that. So without further ado, I'd like to invite the Executive Dean of the Faculty of Science, Professor Stephen Thurgate, to introduce this year's Macquarie Engineering Week lecturer, Mr. Peter Ferris. Thanks, Stephen.
Thank you, Graham. And I've got to say it's a particular pleasure for me to introduce Peter. Peter, as Graham alluded to, has been a very good friend to engineering at Macquarie. As Graham said, engineering started in 2004 and then we kind of restructured a bit in 2006, and Peter had very much a part of helping us go into the community and tell prospective students about how important it was that this role of being an engineer was in our community. So we're very grateful to the role that Peter's played, and here he is again helping us once again, so thank you, Peter. Just a little about Peter. Peter is the General Manager of Planning and Design in the Technology Division of NBN Co. He's held this role since December 2009. He's currently responsible for the design and planning of the fibre, terrestrial radio and satellite networks of the Australian National Broadband Network. This includes generation of the overall network implementation plan and the high-level design for the fibre infrastructure connecting to 93% and the radio and satellite capability for the remaining 7% of the premises in Australia. Before this current role in NBN Co, Peter managed the Network Technology Group at Hutchison Telecommunications Australia through the period of the merger with Vodafone Australia. Up to 2008, he held various positions at Optus, where he was responsible for the selection of the technology used in the Optus network and all its network facilities, as well as the Optus network strategic planning and architecture. He was responsible for the engineering of the Optus transmission network and all its network facilities. Prior to working for Optus, he worked for Telstra and for Telecom Australia in a series of managerial and technical roles for more than 23 years. Peter, and this may not surprise you to look at him, is a life member of the Telecommunications Society of Australia and an ACC accredited Level 2 basketball coach, supporting the Junior Representative Program at Parramatta Basketball Association. As I say, my great pleasure to introduce Peter tonight, and he's going to talk to us about MythBusting the National Broadband Network. Thank you, Peter.
Thank you, Stephen. It's always a great pleasure to be able to talk about things, although if I start to wander into full court presses and a few things like that, you'll have to just indulge me a little bit with that. Again, the NBN is also a very good team, and being part of that team as a high-performing team is very important to me. So while the responsibility for planning the network is mine, we also have a architecture and technology group, we have a construction group, we have an operations group, we have a large number of groups that are all focused on being able to make the NBN a reality and deliver it to Australia. So as a government business enterprise, we execute the policy of the government. So we don't generate those policies, we provide options, and we execute the policy of our shareholders. So that's a very, very important thing to say at this stage. So while what I'll go through today and talk to you about a lot of things, I'm not intending to be drawn on any political debates or any statements of political preferences one way or other. We are a government business enterprise, and our role is simply and utterly to execute government policy. So that's what we're all about. What are we out here to do? We're simply to deliver high-speed broadband to Australia. That's our charter. And what I'll go through today with you is hopefully some of the what I call myths. I haven't got a beret and we're not going to actually blow anything up, and unfortunately I can't shoot anything or explode anything here, but exploding some of the myths and preconceptions may actually head down that path with a little bit of luck. So the framework that we're rolling through is to provide products, and we're not just providing internet for homes. The NBN is about a total paradigm shift in the way broadband is delivered to Australia. It's covering across not just residential, but also commercial and industrial products. It's a total change in this service delivery capability, delivering to consumers, to businesses, and to the industry. So it isn't just about a faster internet. It's about a total change in the way the capability exists to deliver broadband in Australia. NBN Co itself doesn't sell a product to any end user. We're a utility. We're the same sort of people that provide roads and water and electricity and gas. We simply provide the capability to transport data from a location, an end user, to a point of interconnect. That's what we do. We don't provide voice services. We don't provide internet. We just transport data. If I go back to my old roots, we're much more like Australia Post than we are about Telecom Australia. We simply deliver packets. Take them from one point, put them to a point of interconnect. When you would buy a service, if you're fortunate enough to be connected to the NBN in the near future, then you will buy a service from a retail service provider. You won't buy a service from NBN Co. And so the services that all of the different retail service providers put across our network, the innovation that they can deliver, the different products and structures they can deliver, just resides on our transport network. That's what we do. Overall, we talk about delivery to all of Australia. We're not just delivering in the city, we're not just delivering in the bush, we're delivering across 3 different technologies. You will often hear debates about radio, fibre, which one is the best. Many years ago in a particular presentation, I actually got into quite a bit of trouble with one of the previous governments from actually stating that what had to be delivered across Australia was a mix of technologies. You have to choose the technology that's appropriate to deliver the service. And what NBN has chosen is a mixture of satellite radio, what we're calling a terrestrial wireless, an LTE, the long-term evolution that you may have heard of, and of course a fibre infrastructure utilising a GPON, a Gigabit Passive Optical Network Delivery Mechanism. So 3 different technologies, but all interfacing to access seekers, these retail service providers I talked about before, our access seekers, through the same sets of interfaces. So no matter where you would be located in Australia, you could have a fixed broadband service from the same provider if they so wish to do so. Some people that deliver across satellite may not wish to deliver across fibre. Their actual marketing strategy, their service bundles may not want to do that. That's their choice. What we in NBN Co can do is to provide that structure, provide that framework to allow, if a DIDA or an IINet or Primus or Optus or Telstra wish to, they can deliver across all of the 3 technologies through the same points of interconnect. We talk about 93%. We often debate about this. When I looked at some of these figures and that, it's 92.7. That last 0.3% is a real stretch. But by the time we build the network across 10 years, the greenfields will allow us to get to the 93. So I'm a lot happier by people saying 93 these days. But as you can imagine, as you get onto that last fringe areas of the fibre footprint, the cost starts to increase dramatically. And so that's why you change at that point to a different technology to deliver. The chosen technology that we've signed up with Ericsson to deliver is LTE, long-term evolution. We've purchased spectrum from Austar. All of these things are in the press. People know that this has happened. So we have spectrum. We have signed with Ericsson to deliver the fibre footprint across Australia in the next 4 years. And the remainder of the Australian territories and Australian states will be covered via our satellite footprint. We have an interim satellite product that has been launched that is actually covering Australia now and taking over from the Australian Broadband Guarantee. We will launch 2 satellites, 2 brand new satellites, to provide the longer term 12 meg services, 12 meg down services to the population across Australia to enable us to have the coverage that we need to meet the requirements in our 10 years to get this coverage across Australia, 100%. Myth 1. We've actually go through 5 myths tonight, although the end one I had to break into 3 just to talk about fibre a little bit, because again, 93% of the network's fibre, so I've got to talk about it a fair bit. So the first one talks about funding. There's lots and lots of commentary, there's lots of statements about our financial forecasts and it's not funded and there's no business case. There is a public business case. You can go onto the DBDCE website and look at our business case. It's there. What it says is that we have an IRR of 7%, 7.04. I must be a bit more precise given this is an engineering audience. We actually do make a profit. It will take a while. Spending the capital that we need to spend to build a network to every home in Australia, to every business premise in Australia, to every hospital, to every school, will take a lot of capital. And you will end up with the red line going down there to quite a significant peak. But our business case states that it does pay for itself. 7% return, about the same as the bond rate. If you look at the Telstra annual report, most of you may be Telstra shareholders, certainly the older ones probably are. You might see that their rates of return are significantly higher than this. In the time I was at Optus, if I actually went up to present a business case that didn't have above a 25% rate of return, you didn't get much of a audience. So the statement that this network can be built by commercial organisations doesn't allow for these sorts of rates of return. When we talk about the actual framework of it, this is a long-term project. It is a project that cannot be done in a very short period of time. We often talk about scaling, and that one of the statements I often like to use to put things in perspective to people is that 9 women can't have a baby in a month. You know, some things actually take a certain amount of time to go through, no matter how much resourcing you put into it. And there's realistic levels to the amount of resourcing you can put into it. So we have stated this is a 10-year project. And like everything else, it has to have a start date, and our start date is dependent upon the Telstra agreement. Because like any infrastructure deal, our objective is to build the most cost-effective network we possibly can, and to utilise as much existing infrastructure as we possibly can. The PMG built duct work, pits, pipes in our infrastructure here in Australia for many, many years. That was then taken over by Telecom Australia, and it is now owned by Telstra. That infrastructure, to totally replace every element of that, would not have been a sensible way to go forward. We actually did, in our 5 first release sites, model Brunswick in Melbourne, where we utilised Telstra duct, and Wollonga in South Australia, where we actually built our own infrastructure, so that this isn't just an abstract concept. We have proven evidence of what it takes to build a fibre serving area module using these 2 different techniques. We trialled aerial, we tried underground. We have the data to actually back up these particular decisions. And again, that's why it takes a fair while before you start seeing the NBN Co rolling fibre down your streets. If we look at the overall government spend, to try and put it into perspective as to how much NBN Co is spending, total government spending in 2011-12 in the budget, $365 billion. It's more money than anybody can conceivably sort of think about in a time. So you just think about, okay, how does that relate to what they would spend in NBN Co? If we take the $36 billion and a 10-year project and just say simply it's 3.6 a year, then each year this is what it's compared against this current year. So people often talk about the opportunity cost of building NBN Co rather than putting the money into education or putting the money into health. And that's a truism. We're not arguing with that case. But what we're saying is the investment in NBN Co is an investment of infrastructure that will pay for itself, and the additional amount compared to what is currently being spent on education and currently being spent on health in the budgets is not that large. So I think it's a pretty good investment. Myth number 2, we'll never need that much speed or data. Statements like that have been made by different people at different times over the years, and I thought I'd put up a couple of the more famous ones here for people to just peruse and have a look at. Papers often come up with something, and even newspapers publishing things can substantially get it wrong. I think we actually did end up with a useful telephonic device. And I know this is an Engineering Week conference, but even engineers can get it wrong at some times. So the overall framework is making statements about the future is fraught with hazard. And no matter how much people say that they actually want in the future, you need to look at some of the trends and actually see what's happening. And while history, as the financial advisors will tell you, history is no predictor of what's going to happen in the future, these particular graphs have been taken back from data rates back to 1985. So we're looking over a 20-year time period, and they're still heading about correct in terms of the speeds for data that people are wanting and using. If you look at the Cisco modelling, where they're modelling a particular index based on the actual video index across the network and the actual propensity to send video files around the network, these are the sorts of forecasts that they're pushing out. And actually plot some outliers on there where some areas that have fibre to the home already are actually using speeds of that magnitude. If you stretch it over 10 years, and a linear prediction, it starts to get quite scary. Over 20 years, it starts to get somewhat amazing. And even the most conservative predictions that actually show the rates coming down here are still showing that the amount of data, the average data usage continues to expand. And I don't think anybody would be sitting as expecting this trend to go negative. Not unless we have some serious changes in the overall global economic and financial and various other situations. What's driving this thing? Video is a big driver. The interaction that people have with devices these days is very, very different to what was happening in the past. People talk about the iPads and iPods and the mobile types of devices. The bandwidth that they require is substantially greater than in the past. The bandwidth that you require in your home hub to drive all of the devices within your home and all of the connectivity there is substantially greater. So as the 3D movies, they're now a reality. If you talk to some people even 5 years ago that said you would go to a theatre and see things like Avatar, that you would have Harvey Norman selling you a 3D TV today. Those sorts of things are now reality, and they will continue to drive bandwidth. Lots of different applications that sit there. Lots of things that are driving interaction between people in a visual manner. You only have to understand the importance of video by just sitting there and closing your eyes for a second and imagining a world without vision. All of our interactions happen in a visual manner. And driving those through bandwidth, driving those through delivery of technology is something that drives most inventors to try and get that edge to sell that next iPad or such a device. Myth number 3. And this is a most interesting one where we talk about the capability of comparing mobility with a fixed service. NBN Co itself is not offering any delivery of a mobile, transportable, nomadic service. We deliver a fixed broadband service. Our satellite services are fixed. Our wireless services are fixed. Our fibre services are fixed. That's our charter. That's what we deliver. Service providers across those will utilise a massive different number of technologies to ensure they connect to users. And that's where our real strength comes in. But if we actually look at the amount of bandwidth that these technologies can deliver. Now, LTE, long-term evolution, very silly sort of acronym. I mean, we're building LTE. So what are we going to build next year? Extremely long-term evolution, hyper long-term evolution. So we actually have a 4G technology called LTE. That's what we'll deliver. And again, it's utilising a whole string of different techniques to deliver the maximum amount we possibly can to squeeze that wonderful goal of bits per hertz. OFDMA, orthogonal frequency division multiplexing, dividing the frequencies into channels, dividing the time into time slices, closest thing to white man's magic you'll ever see. MIMO, multiple input, multiple output antennas, beam steering, beam shaping, all targeting to get the most you can possibly deliver. Adaptive modulation, 64 QAM, quadrature amplitude modulation up to 64 quadrants in there, delivering the absolute maximum you possibly can, all to try and drive towards that Shannon limit of bits per hertz, all to look at how much can you possibly cram into the spectrum. And if you look at it, what spectrum is available? What can we actually physically do? If we take it from 700 meg to 5.7 gig, we can say that there's 5 gigahertz available for radio. Not all radio, because we've got broadcast TV and AM and a bit, but just what you'd say is basic transmission radio for telecommunications purposes. And of that, 120 meg would be a very big channel chunk for anybody to play with, but just say you got the whole 5 gig to play with. If you look at fibre, one fibre the thickness of a human hair can deliver from 850 nanometres to say 1550. We forget the water peak and different things. We just say that's the bandwidth to compare with 700 to 5.7 gig. That's 160 terahertz. 5 gig, 160 terahertz. There's a lot of difference in the bandwidth that physics just says they're the hertz that you can put bits across to deliver transmission. No matter what developments happen, and there will be continued developments, there will be continued increases in speeds, there will be many, many different ways to squeeze more bits out of that radio spectrum. You got 5 gig, even 10 gig to play with compared to 160 terahertz. 30,000 times more on a single fibre. So again, different purposes, the amount that is available. Myth number 4, fibre to the node. Interesting concept. People talk about fibre to the node being adequate. I hate adequate as an engineering sort of term there if you sort of go through it. I looked up as what it actually means, and I don't think anybody would be really pumped about marketing and selling. We're going to build for the future an adequate solution. We want to build for the future a solution that is future-proof. We want to build for the future many, many different things. Investing in fibre to the node means that you have to have a device that you actually locate out. People have seen these little pillars sitting around. They're Telstra pillars. They connect to about 200 homes. That's where the twisted pair copper comes back to. Fibre to the node sounds a bit sexy. Whenever I describe this, I call it hybrid fibre twisted pair, HFTP. That's what it really is. It doesn't sound as sexy as fibre to the node, but it's hybrid fibre twisted pair. At these nodes that you've got to put in as a box, about the size of a fridge, a bit bigger, next to every one of those particular pillars, we've got to get electricity to it. You've got to get power to it. You've got to have active equipment in there, that the active equipment has a lifetime probably of about 8 years in our general modelling. You've got to have battery backup in there when the power goes down. In other words, you have to build an active distribution network. Whereas the fibre to the home model is PON, passive optical network. It has a huge series of advantages of what happens. Within the fibre network and the GPON technology itself, there is no degradation with speed. There is no degradation of speed with distance. It's a wonderful digital system. It will work up to the 15K and then it doesn't work anymore. You need to change some parameter. You need to change the split ratio. You need to change the optical power lasers. You need to change something to make it work longer. So across that particular bandwidth, it doesn't degrade like DSL. It actually provides you the same speed right across that distance, which is, again, very, very important for anybody that's been sitting out there on the end of a long DSL line trying to actually download a video file. So, myth number 5. And this is the one I had to actually go through and break down into the actual 3 different parts, because I couldn't just let this one go about fibre technology being obsolete in 10 years as just one sort of thing, because fibre technology, what do you mean? So I talk about 3 things. First I'll talk about the electronics, then I'll talk about the fibre, and then I'll talk about the architecture, because they're all important things about fibre. And in terms of the actual, looking at the active electronics, this was in the one of the different presentations very, very recently, where they're talking about 26 terabits per second on a single laser. So as the radio guys have been investing in technology and going through and working through a analog medium to gain the most they possibly can out of the radio spectrum, the optics guys have looked at that and said, hang on, that looks pretty good. We might try a bit of this OFDMA. What about this QAM? We could try a bit of analog across that. When I was first putting in the 10 gig long haul transmission systems, I used to tell people they're just like telex, telegraph, on and off. They just turn the light on and off, that's all they do. Non-return to zero coding, that was it. 10 gig, pretty fast. But they're just like a telegraph, 50 baud, 50 gig, just got to have a quick finger. Obviously, they looked at it and said, hang on, we can start modulating this. So the latest 100 gig systems, they take your 10 gig, overclock it to 12.5, put it into a QAM system to give you 40, or put it into that, and then you've got polarisation on light as well. So you can whack 2 polarisations on there, that gives you 100 gig. So they're starting to get there. Now remember, in the radio we put up 64 QAM. Imagine starting to push the lasers, not just QAM itself as 4, but push it to 64 or 128. The OFDMA, the coding structures. We now have coherent modulation techniques on the long-haul transmission systems. The DWDM systems that NBN Co is now installing, they're from NSN, they are 96 channels of 100 gig per channel. We can go up to 3,000 kilometres without dispersion compensation. These things were unheard of 5 years ago. So the PON system, that the passive optical network system that NBN Co is installing, is an Alcatel-Lucent system, and it's quite a simple TDM-based system, 2.5 gig down, 1.25 gig upstream. We split it across 32 users. It's a power split, so the same signal goes out on each one of the actual feeds, and the TDM protocol handles the time slicing between them. Again, that can be evolved. The basic 2.5 gig passive optical network systems, they're looking at changing the MAC layer, the machine layer, to take it to 10 gig, so to just run it faster. They're also looking at coarse wave division multiplexing systems, CWDM systems, to put 4 different wavelengths on the same physical fibre. So that gives you 40 gig if you do that for 4 10 gig systems. So again, the exact same fibre infrastructure we put in the ground today, we're putting in 2.5 gig electronics. We can change out the electronics to take it up to 40 gig with just changing the end units in the fibre access nodes and the NTUs in the customer's end user's premises. That's what we can do with the existing technologies. There are already systems that Sienna Cell, that NSN are working on, Nokia Siemens Networks are working on, called WDM systems, wavelength division multiplex systems. So instead of using a power splitter, they actually use the cyclical waveguide as a frequency splitter to actually split 32 different wavelengths or frequencies out at the splitter, so that you can actually give a different wavelength to each of the end users. That different wavelength can carry up to 2.5, 10, 40, 100 gig on a single wavelength without changing anything we build in the field. The cabinets that we have that have the passive splitters in them, we can unplug the passive splitter and plug in a cyclical waveguide. Doesn't have to change the architecture or the physical fibre plant. So the capacity will continue to increase as the actual modulation schemes change, the actual framework changes in terms of the coding structures itself, and as we actually change the symbol rates. So there are lots of different ways to increase the capacity on those optical fibre systems. We start to reach the wonderful holy grail of the Shannon limit by going through different modulation techniques, different coding structures. You can see here where the 100 gig systems are now starting to get close to that level, but there's still quite a bit to go. So this is the fibre itself. What happens to fibre? They're digging up glass that's been around in archaeological finds for a long, long time. The actual silica optical fibre, its life is dependent upon generally these 3 factors: the fatigue or stress corrosion susceptibility. That means the fibres in a particular medium. You might say it's a dynamic stress parameter. if it's in water, if it's in an inert medium, then it actually degrades at a certain rate. There's a proof testing stress. When they make the fibre, they actually stretch it. Fibre may have atomic or microscopic cracks in it when it's made, but it's actually tested to a certain percentage, because at that particular percentage, cracks of a certain magnitude will break. So it's tested when it's built. And then there's a install stress. You might call it a static stress. So those two parameters, there's a nice simple equation there that your engineering people can whip up that'll actually obviously give you a straight line or logarithmic graph that looks like that. And a typical value of these types of things is about 60 years. And that again, manufacturers are very conservative when they start stating these lifetimes. I don't know how or what the actual copper lifetimes would have been stated in about 1900 when they actually put some of the copper in our network in, but it's an extremely long period of time. But for this myth itself, 60 is bigger than 10. The NBN co-fibre that we're putting out there will actually be installing a ribbon fibre. Our Type 2 architecture utilises a fibre structure made up of 12 fibre cores, which are actually enabling us to lower the cost of building the network to allow us to splice 12 fibres in one hit, to actually improve the mechanism that we actually put the fibre out in the ground, improving the productivity and improving the actual numbers of fibres we can fit in a specific space. A ribbon fibre itself is quite small. Again, a human hair, picture them stuck together, colour-coded up there. The old blue, orange, green, brown slate that was in the copper network exists in the fibre network as well. The colour code is still the same to identify all of the different fibres. You're happy to note NBN Co will be very green. Our actual fibre will be coloured green when we actually roll those cables out in the ground with our Type 2 architecture for the ribbon fibre. So we'll be able to quite easily identify it. It has a lower profile. The aerial fibre cables you see there obviously are not green. We actually don't want to put them up there green. The black will blend in with any existing aerial power cables, and the profile of it is very, very small. So the size of the cable is about 1/10 that of the current hybrid fibre coax cables that are strung aerially. And again, being totally all dielectric, there is no issue with having to put it on a steel strand, or no safety issue, so we can put it up very close to the power corridor. Okay, fibre technology will be obsolete in 10 years. The last bit of this is the architecture itself. How we actually build the fibre, how do we put it in the ground to ensure that things that we have no idea what's going to happen in the next 20 years, let alone 40 years, that we build it in a manner that can be expanded, that can understand or can be easily changed to suit the way the infrastructure requirements change. And we do that in a modular way where we build particular modules and replicate those as it comes up. Basic framework is a plug-and-play technology. So this was pioneered by Verizon and AT&T in the US in the way that they actually built the Fios network for Verizon and the Lightspeed network for AT&T. And it is a connectorized mechanism where they actually plug in, the actual drop cables plug into these multi-ports, and the multi-ports are connected to fibre distribution hubs in a fibre distribution area. So you have about 200 homes that form a fibre distribution area, and a hub feeds those. The splitters are actually in the hub itself. We then take 16 of these fibre distribution areas and put them into a fibre serving area module, so an FSAM. The fibre serving area module is then grouped into a fibre serving area itself. In the old days, people had understood the Telstra network or the PMG network talked about exchange serving areas, ESAs. Well, we have FSAs, fibre serving areas. So instead of a DA, a distribution area with copper around a pillar, people may be very familiar with those, we have an FDA, a fibre distribution area. So the concepts are very, very similar. The underground structure that's shown here is we have the hub itself with a distribution fibre joint that brings the distribution cable through it, and a local joint that brings all of the local fibres together. In the design itself, we allocate 12 fibres to a particular drop point, where one of those multi-point hubs, you can picture it as a power board for fibre, sits. We allocate 2 fibres to each cadastre, not to a house, but to a cadastre, to the actual block of land. Because what happens in most blocks of land in Sydney now, they knock down the old house, put up a duplex. So if I allocated 1 fibre, what do I do for the next one when there's a duplex? So I allocate 2. Same thing is if that was a business, if it was a bank, they might want a point-to-point fully symmetrical service that needed to transmit and receive fibre. I've got 2 fibres there already planned for it. So for 4 cadastra, 4 areas of ground, of land, we allocate 12 fibres. 4 of them are left spare for what we're calling non-addressable locations. Traffic light cameras, transformers, security cameras, bus stops, advertising signs, base stations, femtocells, all different sorts of things might be needed to be put in there, so the fibre is allocated for it now. We allocate that out because it's 12 fibres. 12 fibres also happens to be 1 ribbon. So in our modular structure, 1 ribbon comes out at each network access point. And then down the street, we have each of the network access points. We have crossroad connections to the other 2 sides. We then build that up in a modular structure for the 200 locations for a fibre distribution area. Again, emphasising this, the fibre distribution hub, which is a passive hub, sits in the centre and feeds fibre out to all of those locations. The actual dimensions are seen there. In Australia, the average house frontage is 19 metres, 2-to-1 ratio, 38 metre depth, 19 metre front. You can look at it then, when you build up an FDA in this nice averaged modular manner, you end up with about 1 kilometre of fibre from the FDH. Some of the hubs tend to get personalised very quickly. This is Brunswick. As you can see, they were very keen to make sure that they could put their name on it quite quickly. Building it down the streets, again, very challenging. Even in Brunswick, which was a Telstra infrastructure build, we had to do quite a lot of replacement of pits and augmentation of the actual infrastructure that was there. Aerial infrastructure, where there is no Telstra underground infrastructure and there is aerial power, then we'll actually use an aerial delivery. In the aerial delivery itself, it's exactly the same framework. Fibre distribution hubs, the 12 fibres or 1 tube per 4 blocks, that gets put on the pole itself in a multi-port that actually drops down to each house. Again, same modular structure for the fibre distribution area itself. Overall, you can see that the fibres are placed up close to the LV. It's an all dielectric self-supporting cable, and the infrastructure can be placed in the LV corridor, not the power corridor. What that does is absolutely minimise the visual impact that occurs for building this particular infrastructure. It's nearly indiscernible from the actual power cables that already exist. And NBN Co will only do this where there is aerial power. I've said in many different forums, NBN Co does not plan to install poles. Again, that's one of the multi-ports I talked about before, so they come in sizes of 4, 6, 8 and 12. And again, they're like a power board for fibre. You simply plug into one of those sockets and the drop goes down to the house where the network terminating unit is located. The fibre serving area module. So we have these groups of fibre distribution areas of 200 homes. They're placed into an array of 16, and a dual loop structure allows the feeder fibres to be placed in those distribution tubes to go out to each one of those hubs. The dual loop structure allows us to have a geographically diverse path from any particular hub back to our fibre access node. So if the actual cable is cut there, a service that was in there as a business grade service, so a hospital for example, or a school, would actually have the capability of having a path in both directions. An individual house is built as a tree structure from the fan site. The fibre access nodes themselves have geographically diverse protection back to the point of interconnect, but there is a non-geographically diverse path out to each house, so what we call a tree structure. The feeder fibre goes out to the hub, there's a splitter in the hub and a single fibre out to the house. In our Type 2 architecture, there is a return path for the feeder fibre back to the fan, but it is not automatically switched in. It can be manually patched in when it's required. Again, then, these particular hubs, or these particular FSAMs, or fibre serving area modules, are then grouped around a fibre access node to actually provide us with the overall fibre serving area, the FSA. So maximum size of an FSA is 38,400 or 12 of the FSAMs. And again, a lot of these modules have been tailored to suit the Telstra exchange infrastructure and the Telstra duct infrastructure so that we can maximise our use of the existing Telstra infrastructure. So overall, again, from a house, we come back through our local fibre network, our distribution fibre network to the fibre access node, and then with geographically diverse paths back to our aggregation node that actually holds our points of interconnect. So over Australia itself, because we have close to 1,000 fibre access nodes, fan sites, and we have 121 points of interconnect or aggregation nodes, then we still need to have a transit network that's quite extensive to actually collect the data and bring it back. For example, in the Northern Territory, the aggregation node is in Darwin. So from Alice Springs, we have a path back to Darwin for the traffic, and then a protection path which goes all the way around there. And again, to ensure that we have a geographically diverse protection path for each of the fibre access nodes back to the aggregation node to its parent, we have to build these particular geographic rings. And again, all of these rings are predicated on being near population centres. We try and collect as many as we possibly can. Our planning rules were that every town in Australia that had over 1,000 premises, we would fibre. They were our seeds. And then when we built the transit transmission paths, if a town was on or close to a transit transmission path, if it had over 500 premises, we would actually connect it to. So they're not people, they're premises. So we work on things called GNAFs, Geocoded National Address File Locations, and they are our planning rules for connecting this particular network together. So again, overall, 121 points of interconnect. That was a policy decision from our government itself that we are now implementing. And that's about it.
Thank you very much, Peter, for a fantastic talk. We have a few minutes for questions, so I'd appreciate it if you could raise your hand and wait for the microphone. That gentleman.
Michael Clark from TELUS Australia. I'm interested in the existing network. We have two fibre optic cables. In fact, in my place there's two fibre optic cables that goes past us, one from Optus, one from Telstra. They're hanging on the poles, they look ugly. I'm just wondering what happens to those. Are you going to utilise that infrastructure, or are you going to suggest that it's removed and replaced with the new infrastructure?
Because NBN Co doesn't own that infrastructure, it's owned by those particular infrastructures, the hybrid fibre coax network. You've probably got a bundle of fibre and coax, so it's probably a bundle about this big on a stainless steel strand lashed together. That's owned by Optus and Telstra. What they decide to do with their networks, I'm sorry, is their business. It's not our business. We have a deal with Optus for them to migrate their traffic off that hybrid fibre coax network to our fibre network when we roll it out. We have a deal with Telstra for them to migrate their traffic off. Telstra will not migrate the video from Foxtel off. What they decide to do with that network, as again, it's their business case and their decision. It isn't ours.
Okay, thank you.
what's the role of kind of experimental technologies, like, for example, the two technologies being developed by CSIRO at the moment, the access and the backhaul technologies, and how would those technologies ever get into the NBN? What's the path that they would ever get into the NBN?
Yeah. I have a colleague in Melbourne, that's Tony Cross is his name, who's the General Manager of the Architecture and Technology Group, and he runs a process called the SDF, the Solution Delivery Framework. So from the business requirements that come up with an NBN Co, those requirements, he goes out and finds solutions from them. And again, NBN Co, we're a government business enterprise. We're probably fairly risk adverse. So the GPON technology we're utilising now is tried and true technology. The passive optical network technology is tried and true technology. There is XPON, for example, out there now, which is 10 gig that Verizon is installing in the States. We're not installing that now because we want to wait till it is actually proven. The LTE technology that we're using for our fixed wireless network, there's installations of that around the world in many, many different places, and it's been trialled by all the mobile carriers. So it's probably the closest we would get to a bleeding edge technology, and that's being provided by a vendor such as Ericsson as a managed service provider with all of their guarantees behind it. So again, it's only my opinion of it, but the CSIRO needs to move their technologies through a whole marketing stage, picked up by a productization company as one of the major equipment suppliers that would then be able to manufacture it and supply it and warrant it before we'd look at it.
Would it have to be a part of a worldwide standard?
I think nearly everything, to be risk adverse to it, the standardization proves it can keep going. If you look at some of the iBurst technologies in radios and some of those things that were promoted as quite high, but now they've been submerged, even the debate between WiMAX and LTE and how they go through, going with a non-international standard technology is very risky. The NBN Co, as I said, we have a role to play to roll out a network to 100% of Australia in 10 years. We really can't afford to be just a laboratory or an experimental area. We need to put it in perspective with this. It's often sort of talked about with NBN guys. If you see somebody in an aeroplane staring out the window looking terrified, it may not be that they're afraid of flying. They're actually an NBN Co exec counting windows. 1, 2, 3. Because we have to connect 6,000 houses a day, every day. If it rains, we've got to catch up. If we get behind, we've got to catch up. We have to do that for 10 years. And that is an incredible task to set before anybody. And so to layer that with an experimental technology and looking at those aspects of it is very, very difficult to do.
Hi, Nick Costa from Brainmates. I'm curious, what other bottlenecks you see impacting the performance of the NBN that's outside of the NBN, like international traffic or networking protocols that might get in the way?
It's a very interesting question in terms of the performance. That's not so much the performance of the NBN, but that's the performance of the customer experience or the end user experience across the network. Our customers are the retail service providers. Their end users will have a huge number of factors influence their experience. We sell two parameters to a retail service provider, an access seeker. We sell an access VC and we sell what we call common connectivity VC, a CVC. So if the retail service provider or access seeker does not dimension their network satisfactorily, they have to connect for a national service to 121 points of interconnect. They have to provide the services to those end users. If they don't have the caching, if they don't have the internet connectivity, if they don't have the international connections, then the end users will have a degraded experience. Now, for us, that's not good news, but we're only a utility. It's like if you happen to have a gas stove, and wonderful, you can spend probably $6,000 on putting a wonderful gas stove in, but if you still burn the souffle, you can't blame AGL. They just provided the gas. Somebody else has got to do the cooking. So we're a utility. We just provide that transport. So if our network does what we warrant it to do from the network terminating unit to the point of interconnect, that's what we have control over. We will try and ensure that the retail service providers provide enough connectivity, but we can't force them to. We can only provide that transport. It's almost like the highways and tollways. You can't blame the tollways for the cars that drive on them.
It's like a Maserati with a 60 km/h speed limit.
That's right.
Okay, thanks for your questions. I'm sorry there's a few more, but we'll have to call the proceedings to a close, and let me start by at least declaring those 5 myths well and truly busted. Thank you, Peter. Okay, before formally closing the proceedings, I'd like to again call on Professor Stephen Thurgate to formally thank Peter for tonight's lecture.
Thanks very much, Graham, and I really enjoyed that. Peter, it certainly dispelled some obvious myths that were running around my head. But that was terrific, and what an exciting project, what an exciting vision of Australia. I think it's really quite breathtaking, and it's great to see it being implemented in such a logical and consistent and well-engineered way. As a little memento from tonight, we'd like you to accept this.
Thank you very much, Steve.
Okay, well that concludes the proceedings for the evening. Thanks again for coming along. I hope it's been enjoyable. And on the way out, I've been advised that you might need to push a button to get out the second set of glass doors on the exit. So thanks again, and see you around.